Hello, everyone. This is Amir from Audio Science Review. We're going back to school on the technical topic, namely electrical grounding. I'd say there's no more misunderstood concept than electrical grounding. And even engineers get this wrong. I can tell you that when I went to engineering school, I wasn't taught this. And even when I practiced this engineering, I wasn't taught this. It's something that it can be explained very simply, but your intuition gets you in trouble. So let's go through some of the myths that people have. And the top one is really what many audiophiles think, and that is the fact that they think that you can take equipment noise and drain it into the ground. They have this, common intuition that says, when I'm in the sink, I turn on the water and the water drains into some place and it goes away. Therefore, same thing must happen with electricity and noise. And of course, noise is not good. And oh, by the way, I hear the lower noise floor, blacker background, but you can't measure that. So we'll go through what's wrong with that argument. The corollary of that is that you can, if a ground is a good thing, maybe you should have a dedicated one for your audio system. And if you're going to have a dedicated, electrical circuit, might as well have a dedicated one for your audio system as well. The third one is this notion of star grounding. This is a real thing, but people think, all I've got to do is star ground all my equipment, and I can never get ground loops or hum, and then this noise can't happen. So they go plug everything into one outlet or one shared ground, and they expect that to solve their problems. Let me tell you that some of these are illegal. You're not allowed to do them, and they're all completely wrong. And I'm about to explain why. Now, instead of me explaining all these things, I highly encourage you to go look for writings of Bill Whitlock. He's president of Jensen Transformers, which sells transformers for creating balanced circuits. But he has one of the best explanations of why these concepts are wrong. This is a presentation that he has made at Audio Engineering Society chapter, but he also has many other papers, many other online tutorials. He teaches classes. He is by far the expert in this thing, and he has a way of proving his points that just ironclad, and the proofs are so simple electrically and rely on such simple physics that good luck trying to argue with him. Not because you can't argue with him, but it's just, you have to think, you have to argue that the aliens exist before you can prove him wrong. So these concepts couldn't be more correct, but misunderstood and not known. So remember this name, Bill Whitlock. He's been kind enough to give permission here for people to give his presentation. The actual presentation is about 100 pages. I'm not going to put you through that. Just a handful of slides I'm going to borrow from him because I'm too lazy to draw the diagrams as written and drawn. The most important concept that everybody needs to understand is that electrical circuits have to be completed to become a circuit. So take a battery like this. It's got a positive and a negative terminal. If I hook up a light bulb to the positive terminal, will the light come on? No. The light bulb needs to be connected to positive and negative. And when I do that, then a circuit will get completed, and I'll be able to light up the light. If I don't do that, nothing happens. If I just hook up a wire to the positive terminal like this, nothing will happen because the wire is not going anywhere. So current can't flow, and if current can't flow, the battery can't drain. So it just sits there, does nothing. So this comes back to this notion of, can you drain noise into something with just one wire? Noise is a voltage source, just like this. It's a signal. And it has to be completed. It needs to have a path for it to do something. So a single wire transmission does not work, unless you want to build an antenna. But otherwise, it just does not work as something that completes the circuit. I won't get into the rest of these for now. Some of it is I've sort of implicitly covered, but so let me cover the last bit of it. If anybody ever doubts you and you can't, follow repeat the arguments that I've made, just tell them this. Ask them, if you need grounding, noise needs to drain into the ground, physical soil in your home. How is it that airplanes have no trouble having extremely sensitive electronics with no noise, right? They have transmitters, receivers, avionics. All that works. You can have audio systems, quiet. How about in a car? Car doesn't have a connection to the ground, right? You don't drag a chain behind your car to get quiet sound, right? So know that noise is not something that requires earth to work. Okay, now the earth can cause, the grounding can cause problems, as I'll cover, but just erase this notion that earth is a place where you store noise, that you dump noise. It's not how it works. And I just gave you 2 existence proofs of how real life circuits work without that dependency. To fully understand this topic, you need to understand how our AC delivery systems work. Unfortunately, I don't have knowledge of how they work overseas, but I imagine the concept is similar to what we have in US. You have AC transmission is high voltage, comes down, at some point goes through a transformer and steps down to 120 volts, and you get 2 of these coming in to your residence in US, at least modern wiring. This can be rated at 100 amps or 200 amps or whatever you have coming in your service entrance. That large amount of current then gets divided up in your breaker panel into different branch circuits at their rated amperages. So most common in US is that these are 15 amp and each one was protected with a breaker. So if it sees more than 15 amps for a few seconds, it will trip, or if it sees a lot more than 15 amps, it'll break a lot sooner. So this wire is called the line or the hot wire, and it's black, comes in and it connects to one of the pins in your outlet. Then there's a second wire, which is the center tap of this transformer, and that's called the neutral, and the neutral connects to the other pin. Your equipment has hot and neutral going into it when you plug it into this outlet, and it then creates a circuit where current flows from line, goes into the equipment, goes through the neutral, and comes back and completes this path over here. So things are constantly moving between these 2 lines. There's a third wire that comes from the same point that the neutral came, and it goes to this center pin like you have in these outlets, which is this, what I call safety ground. Okay, so you have a third pin in here, and that's the safety ground. That wire is green by convention, but it plays no role in what I just explained. The only current that flows right now is between line and neutral. The ground wire is sitting there doing absolutely nothing. And it's basically a redundant path to the neutral wire because they both go to the same place, right? Neutral goes in here, ground goes in here. Okay, so remember that. This ground path did nothing for you right now because all it's done is connected to a chassis of your equipment doing nothing. Okay? Now let's talk about what the ground wire is used for. Let's say this hot wire, the line wire inside your equipment, comes loose and it connects to the chassis of your equipment, which usually is metal, right? The moment it does that, your whole chassis is now energized. And if you touch that, if there was no other protection mechanism, you touch that, you get an electrical shock and you could die. So very serious risk in there. So to remove that risk or lower that risk, we take the chassis and hook it up to the third pin of this outlet. And that becomes our ground and goes to the same spot. Now imagine this has happened, this hot wire has come loose, it's connected to the chassis. The chassis is a stout piece of metal, so it has almost no resistance to current. So now we have basically a short circuit. Hot wire comes in here, immediately connects to ground, circles back, and goes through and completes this circuit. With 100 amps on tap over here, this circuit now all of a sudden goes from maximum 15 amps to 100 amps available to it. And this breaker here, boom, it'll open up. There's a little bit of delay in there, and it will open up. So as soon as this comes loose, connects to the chassis, boom, this disconnects, and the hot wire is no longer hot, and therefore your chassis is no longer hot, and you're not going to get a short. You're not going to get electrocuted. The equipment doesn't work because this has come loose, but we have triggered the breaker to come on. So the key is that now the ground wire becomes completing the circuit in here, not the neutral wire, and that is why it's there. It's a form of redundancy, and it's for safety. Notice what Bill has circled in here. The fact that this was hooked up to the ground, to dirt outside, there was this ground rod that went to the earth outside, has absolutely nothing to do with this path, right? This path was here from the ground, going in here, boom, and the breaker broke. Nothing went down to dirt. Why does it not go to dirt? Because remember, there's no circuit in here. Where would it go from here? There's no path for it to go. Electricity likes this path because it's got the least impedance, as we call it, and it goes right here. Say, hey, I'm going to complete this circuit. Why would I go this way? Where to go after this? This ground rod is in here in case of a lightning strike to the wiring that's upstream of your this transformer and your feed. Should that hit there, there's a path in here that will bring it down to ground because those poles also are grounded. So some of that energy gets shunted down, and I've covered surge protectors and things later on, but that's the only thing this thing is supposed to do, is deal with these surges from lightning strikes externally coming in here. It plays this ground rod that's outside of your home, plays no role either in normal operation of your system or in the event that this is shorted out. Okay? Now let's talk about what the audiophile goes and does. He goes and hires people and spends a good bit of money, this is not cheap, to put a stout ground rod in there, or maybe multiple rods. He goes researches chemical bonding and grounding, and there are all kinds of schemes in there, and builds himself a great ground for his audio system, and whether it's one outlet or more doesn't matter. So now his ground is connected to this. He naturally disconnects the ground that used to go to the main service panel, because that's the ground that he's trying to replace with a better one. Now let's follow what happens when we have this same short. The hot wire comes in here, connects to the chassis, connects to the ground, goes to the ground wire, but it can't follow this path anymore because that's disconnected. Where does the electricity now go? To this new ground rod that he has installed, and it now wants to complete the circuit. So where is the circuit that exists between these two ground rods, right? One is on this side of the house, the other one's on the other side of the house, maybe 50 feet away. You think dirt and vegetation and rocks are great conductors of electricity? They are not. The impedance in here could be good, 10 or 20, 30, 100 ohms. I mean, it depends on how bad, on what the condition of your soil is. And because this impedance is high, a lot of that current can get lost in here, dissipated in here. The power can be dissipated in here. So as a result, what carries through this path now can be low enough current that this breaker will not trip. It will not see necessarily 15 or 20 amps to break. It'll stay conducting. And if that stays conducting, it means the energized chassis of your equipment that's now at 120 volts continues to be at 120 volts. You touch that, you can die. For this reason, the National Electric Code, NEC in US, does not allow you to have more than one ground for a premise. From here on, from this line on, you better have a single ground, and this is your ground. You cannot do this. This is against the code, against safety, and there's no reason to do it. It doesn't do anything for noise anywhere. Remember, if there's noise in here and you connect it in here, what's it going to do? Where's the circuit that it's going to go to? There isn't any. Noise will not want to follow this path. It is not a path that he likes to follow because it doesn't go anywhere. Okay? So do not, please, do not go do these unsafe things and waste money. If you've done it, you need to undo it. You need to disconnect this ground and connect this. You can go waste money to make a better ground in here, but that's only good for lightning strikes and what have you. It has nothing to do with the performance of your audio system. Okay? Now, Here's the tough part about this. No matter what you do, you could have the safest, cleanest installation, best wiring in your home, and you can still have hum and ground loops. Remember this. Even in the safest, best implementation, you can have ground loops. Why can you have ground loops? And let's see, yeah, I've got another slide. When you have multiple outlets in your home, you can never assure that these two safety grounds are at the same voltage potentials. So there's always some kind of voltage differential between these outlets, and no matter what you do. So keep that in mind. You cannot have zero potential system. And this gets a little complicated to talk about impedances and things like that, but there's no such thing as zero impedance and zero voltage. Indeed, up to 3 volts can be allowed, and I've got a little instrumentation special meter you can get, and it'll show you that you have a voltage drop differential between these outlets. So remember that even in a fully code compliant premise, you can still have differential between these outlets. So what does that mean that I have this differential? We have 2 types of interconnects in our audio equipment. We have RCA or unbalanced connections, or we have balanced or XLR connections. What's the difference? In an unbalanced connection, remember, we always need 2 wires to complete a circuit. In unbalanced, that second wire, this is a signal wire coming out, the second wire is also the same as your chassis of that safety ground. Remember what was hooked up to? That is also used as a reference for these 2. So this output is reference to this, relative to this. With a differential or balanced output, sorry, I shouldn't have said differential, that's something else, related but not exact here. The 2 signal wires that are used to transmit have no connection to the chassis. And I'll show you in a second, when you don't have that, then it does not matter what the voltage difference is between these 2 chassis, whereas in here, it does. So far, I've been talking about 3-pin AC outlets, but many devices come with 2-pin, and the code allows that as long as there's enough safety measures in the equipment where that kind of short that I showed does not exist. Now, you might think, well, okay, if that doesn't exist, the chassis, therefore, should be at 0 volts. No. There's this thing called parasitic capacitance. There's a way for electricity to still travel from your AC wiring to the chassis and energize it. You ever touch the laptop or some device or shaver or something that's plugged in and it gives you a little buzz? Those are almost always double insulated, so have 2-wire connection. Why do you get that buzz? That's actually a mild electrical shock. The code allows some amount of leakage, where some amount of that voltage can couple to the chassis, but it limits the amount of current in there to a level that won't kill you or won't hurt you. But it does not guarantee that it's 0. Because, and when it's elevated, it can be high enough where you feel that buzzing sensation when you touch it and it feels like a mild electric shock. Well, the moment you have that and you have this unbalanced RCA connection, this voltage and this current can actually now travel between these 2 chassis, and it superimposes on top of your music signal. So your music signal is playing from the transmitter to the receiver, but you also have another one that is AC and all of these harmonics traveling along with it for the ride. Those 2 get combined. The receiver doesn't know the difference. It thinks both of those are your music, so it plays your music, plus it plays a hum on this thing. Now, Bill says typically this is not a problem because, unless your interconnects are long. This is not the case. Because of our long audio chains we have these days with computers and then external DACs and then downstream devices, you could get in trouble pretty quickly, even with short wiring. And indeed, many people do. They have short interconnects or just a little amplifier and DAC on their desktop that's AC mains powered, and they're hearing buzz and hum. So just know that this notion of using RCA unbalanced connection is just faulty to begin with. Okay? And that's what this talks about, that the tiniest amount of flow in here doesn't need to be much, can cause this kind of noise and hum and buzz that gets communicated. The proper way to do it, and what a real audio interconnect should have been years ago, is this balanced connection, which is typically driven also differentially, and I won't talk about what differential means. But the key in here is that you can have now current flowing between the two chassis because they're sitting at different voltages, but it means nothing because it is not part of the signal communication. The signal communication is between the two wires that are transmitting between a receiver and transmitter, and therefore it is not impacted by this ground noise. The hum and buzz can continue and there's no problem there. Okay, so just to give you some personal insight, I measure tons of audio electronics. About 90% of the time, when I measure something with an RCA connection, I see contributions from mains. I see 60 hertz in US that we have. If I were measuring in Europe, I would get 50 hertz. And I'd see it, also harmonics of it, 60, I may see it 120, 180, and so forth. And but whenever I measure differentially, with balance, 99.9% of the time, there's zero contributions. So you have to assume that every piece of equipment you have currently has ground loops in it, and what we call this ground loop because remember, it's a circuit, and that there's ground noise. Why do you not hear it 99% of the time? Is because our threshold of hearing is quite high, and this noise level is below threshold of hearing, so we don't hear it. I can measure with my instrumentation, but you don't hear it. So what has been a broken architecture has survived all this time because we basically don't hear it. If we heard it, we would never tolerate it. We would have gone to this kind of differential system. Again, a balanced system. So that was the presentation. So bottom line, the safety ground in your equipment is for safety. Do not go put in another grounding system or go spend money on grounding doodads and wires that go to grounding buses. There are people who sell you a box with dirt in it, with a probe in it, thinking that that's a ground, just like you're outside. If I just put a metal inside some dirt and sell you as a box, that's grounding things. Yes, you can plug that into your system. That usually has one wire connection. That's a telltale sign that something's wrong. And people connect that to the chassis of their audio equipment and immediately notice improvement. The improvements in your head, you're paying more attention, you're drilling more into the audio, and all of a sudden you're hearing more detail. None of that has anything to do with that device. As I always say in my videos, have someone connected, disconnected, see if you can tell when they've done that. I guarantee you will fail. Have them go behind the equipment and not tell you whether they've connected or not, and you guess whether, if it's so obvious that the veil is removed and the noise floor is improved, then you should be able to tell. None of us are watching, by the way, so it shouldn't be stressful. Just have somebody else do the plug-in, unplug-in. Do it 8 or 10 times, see if you get it right every time. I guarantee you will not notice a difference. Please don't do things that are, safety hazards like, secondary grounds and so forth. Okay, hopefully this made sense. I thought it's an important topic to cover. If you have questions or concerns, raise them in Audio Science Review thread. Would probably be easier than trying to answer them in YouTube with just, a few words here and there. But it's an important concept from safety point of view and from fidelity point of view. Okay, see you in a future video. Bye-bye.